Welcome to Homework Lib.
Chapter 14, question 120. The gas phase reaction of NO with F2 to form NOF, and F has an activation energy, EA, 6.3 kilojoules per mole, and a frequency factor of A, 6 times 10 to the power of 8. The reaction is believed to be bimolecular, and this is the given reaction, so they want us to calculate the rate constant at 100 Celsius. So let's draw the Arrhenius equation. Arrhenius equation is going to be K equals to A e to the power of negative activation energy over RT. Now, what are these values? Energy of activation is 6300 joules per mole. We want joules for the unit, and R is going to be 8.314 joules per mole Kelvin, and RT is going to be equal to 100 Celsius plus 273 for Kelvin. So it's going to be 373. And lastly, Ra is going to be equal to 6 times 10 to the power of 8. So if I write these values into the equation, R comes here and T comes here, and solve for K, K is going to be equal to 7.8 times 10 to the power of 7. Now, draw the Lewis structures for NO and NOF molecules. For NO, we're going to have 6 electrons for oxygen outer shell and 5 electrons for nitrogen's outer shell. If we add them together, what we're going to have is 11 electrons. Let's distribute that. 2, 4, 6, 8, 10, 11. Now, this is not a good model because what we want is an octet rule that is at least going to be close to octet rule. So the oxygen has 8 electrons around, but nitrogen has 2, 4, 5 electrons around. If I move this lone pair over here, what we're going to get is the closest to the octet rule, where we have 7 electrons around nitrogen and 8 electrons around oxygen. What about NOF? Now they give a hint that's misleading because central atom is nitrogen. So O and F would be correct. But what we're going to have 6 electrons for oxygen, 5 electrons for nitrogen, and 7 electrons for the fluorine. So if I'm going to distribute these, I'm going to have 2, 4, 8, 10, and 12, 14, 18. Well, this is a model. What we can do is we can make this prettier and calculating these electrons again. 8, 10, 12, 14, 16. I'm missing 2 electrons. I can add these two right over here. But nitrogen is not following the octet rule. So if I move this lone pair and check again, oxygen, double bond, nitrogen, single bond, fluorine. Now if you count them, all of them are going to be obeying the octet rule, 8 electrons around all of those. So if you look at the part D, the possible transition state for the formation of NOF. So we want to form this, and what we want to do is we want to use these two. So let's use our NO. I'm not going to show the electrons around the molecule. I'm just going to show the bonds. This is what we have and where we want to go using fluorine. We want to go to O double bond and single bond F. Now what happens is, as you can see, N double bond O is not changing. What changes is we don't have a fluorine-fluorine bond anymore, and we have a single bond between N and F. So what we can do is N double bond O dash F dash F. So this is going to be formed and this is going to be broken. So this is a good transition state. Over here, I think I forgot answering the part C. Predict the shape of an OF molecule. So they're asking us the shape for this. So this looks linear, but it is actually not linear. The reason why is there's a lone pair right over here. So this is going to push these two bonds down. And what we're going to get is a bent shape that is like this. We call this bent. And lastly, suggest a reason for the low activation energy for this reaction. So these two molecules are in gas phases, and gases are the most active state of a matter. We could have them in an aqueous solution in liquid, but they're not as fast as gases. Also, these are very volatile, so the rate of these two molecules finding each other and forming a reaction is going to be very fast. That's why I think the activation energy is pretty low for this reaction.